that was going up to NRG 292, but like I said, I'll get an email with that YouTube link, and I'll put all of these inside the shell. Okay, so we just got done talking some kind of big picture transportation issues, talked a little bit about force, talked a little bit about miles per gallon. So let me get into the Shell Eco Marathon and tell you a little bit more about it and what my experiences have been. Oh, and just, I guess since this came up, I wasn't planning on it, but that's a picture of me pedaling a human electric hybrid. So the thing's got pedals, it also has a motor. Those are my children, and so previously when I was at Drexel University, I had a couple of these pedicabs, and they were great things to play around with for vehicles of this nature. So what we'll see when we get into the Shell Eco Marathon, the maximum vehicle weight is about 500 pounds, and we're going to be dealing with horsepowers on the order of just 1 to 10 horsepower, even not like we see in the big combustion engines we see. But anyway, it was a lot of fun. It was also a good economics lesson for me, because I just kind of went out cold into the streets of Philadelphia and pedaled this around. Didn't have a posted fare, but just allowed people to sort of pay what they felt was fair. And it was a wake-up call, how little human power is actually worth. I was just like, man, I am working my tush off, and I'm getting this, kind of $5 or whatever for this ride that took, better part of, maybe 30, 40 minutes. I'm like, man, this is a tough way to make a living. So, I don't know if you remember the whole John Henry song about, I'm going to die with a hammer in my hand. It was, back in the steam engine days, and, the man competing against the machine, and that I felt a lot like that, and I was sort of losing this battle to the machine. But again, just a little bit about my own philosophy. You can see that I call my company Human Powered Future. It's a professional limited license corporation. I'm just a sole proprietor and provide engineering services. But really the idea behind this is that, gosh, if you can do something on your own, why waste the machine's energy? Why waste those precious fossil fuels or what have you? Just be your own machine kind of thing. And that's why I tend to take the stairs and ride my bike and do more with less, I guess. So anyway, that's the reason behind the name. Okay, so let's hit the Shell Eco Marathon. Website. We'll truck around that. And you might hear me use the acronym SEMA, S-E-M-A. There are several Shell Eco Marathons around the world. SEMA is just Shell Eco Marathon of the Americas. And historically, it's been held in Houston. Last year, it was in Texas. Or I'm sorry, historically, it's been held in Houston, Texas. Last year, it was held in Detroit, Michigan. The University of Montana did not compete last year. We were doing engineering, more or less. And the primary reason for that is in 2012, we competed, and in fact, I'll just bring that up while we're looking at it. This is our 2012 team. We competed in the solar division, and we competed in a division that was called the prototype. Now, in the prototype, it's a car that has to pass sort of a minimum number of safety requirements and just operate the track. Obviously, you wouldn't take this thing out on a road. Its top speed was about 20 miles per hour. So having very low acceleration and very low top speed can kind of leave you a sitting duck in traffic. So this was the prototype. The division that we attempted to compete in 2014 is called the Urban Concept Vehicle. The Urban Concept Vehicle has to be street legal. Horn, windshield wipers, no airbags, but just something that, you know, you would feel safe in normal traffic. So we spent last year, rather than competing in the 2015 event, we spent last year doing a lot of the engineering and a lot of building for a more sophisticated vehicle, and we made a lot of good progress on it. So in the third chunk of the lecture, I'll show you that. But for now, I just kind of want to show you a big picture in terms of the Shell Eco Marathon. And this was a solar car. There used to be a solar division. There's no longer a solar division. And I'll tell you why. Let me just segue into that. I'm going to see if I've got a... So when I was on the faculty at Drexel University, we actually won the solar division. And let me see if I can get an image here.
That's out the whole U.S.
Yeah. And we, so there it is. So this is one of my students there in the vehicle. I think this was, I think these, so this was actually in National Geographic. And part of the reason it was such a big deal is we beat Purdue. You know, and Purdue is a bigger engineering powerhouse. You know, nothing against Purdue, but the solar array that you see there on Purdue's vehicle, actually just the cells themselves cost more than the University of Montana's 2012 budget. You know, build, travel, everything, just the cells. And again, nothing against Purdue, but they enlisted a lot of help from Boeing, from some high-end engineering firms that actually did a lot of the build for them. And as it turns out, that was a little bit of their Achilles heel, because when something went wrong, having not built the technology themselves, they weren't capable of fixing it. So as you can see here, the solar cells on the Drexel vehicle, and we still here in the back of the classroom have some of them. They're just individual cells. You might have seen them outside my office also. They're like Pringles potato chips and super fragile. I mean, you look at them, they break. But we were able to solder them together. So this was what was going on at Drexel, and we used a lot of that same methodology when we built our solar panels here at the University of Montana. So that's a little bit of history on the University of Montana team. Getting back to that big picture lecture that I just gave, one of the requirements for actually winning the solar division, there's a few. One is that you have to maintain an average speed of at least 20 miles per hour. You don't have to be above 20 miles per hour the whole time. And in fact, what we'll see with a lot of the internal combustion engines, it's typically to their advantage from an efficiency standpoint to speed up and slow down. Because if you've ever ridden a motorcycle or driven a stick shift, you'll notice that typically most vehicles have sort of a sweet spot or a power band where the engine is operating at its maximum efficiency. So rather than sort of like idling along at a low speed that is suboptimal for efficiency, it's sort of better to get up into that power band, spend a certain amount of time there, and then coast for a bit. With the solar car, you might consider a similar strategy where it's like, hey, it's really sunny out, let's go and get our average speed up while we've got time. The downside of going fast is typically your miles per gallon, or your miles per gallon equivalent. Or you could think of it in terms, or another way to think of it would be kilometers per megajoule. Distance traveled per energy is going to go down the faster you go. In general, and as it also turns out, right around 15 or 20 miles per hour is the speed at which the rolling resistance drag, so it's the drag between the wheels and the road, equals that of the aerodynamic drag. So you basically have three general components of where you're losing energy in the system. One is just in the transmission. Obviously parts are moving, things are getting hot, you're losing energy there. There's drag between the wheels and the road, you're losing energy there. And then the third one is losing energy aerodynamically. Typically, the rate at which energy is lost with the road is linear. So if you double your speed, you double the rate at which energy is bleeding from the system. In terms of aerodynamic drag, the relationship is actually cubic. So if you're going 3 times as fast, you're going to be losing 9 times as much energy in general. And it's somewhere between quadratic and cubic, but right around 15 or 20 miles per hour is where that linear line and that linear curve and that quadratic or cubic curve cross, and we can get into that in a little more detail. But you can see, that's kind of what. There's a couple reasons for only going 20 miles per hour. One is it's just safer. As a lot of these cars are not all that reliable, and parts are flying off, and the steering comes loose, or the brakes don't work, or whatever. And much better to be hit by a 500-pound car moving at 20 rather than a monster truck doing 70. So that's part of the reason there too.
The quickest to finish that length?
It's not the quickest to finish. It's a great question though. On the solar car, you're given, on all the vehicles, you're given what's called a joule meter on the electric cars. And the joule meter is just measuring the voltage at which the vehicle is operating and measuring the amps that are flowing through it. So volts times amps equals watts. That's basically your miles per gallon. So at the end of the time, you'll integrate that, add up all the megajoules, and then at the end, it's the megajoules per kilometer that end up winning. So the lower megajoules you consumed for the whole distance. So to finish the race or to win the race, you do have to complete the whole 6-mile course, and you also have to maintain at least 20 miles per hour. So there's no incentive to go faster. And as I said before, going faster typically reduces your mileage, so it's usually to your advantage to go as slow as possible, and that as slow as possible is 20 miles per hour. So with the joule meter, and again, this is somewhat of a moot point because the solar car division is no longer part of the competition. Part of that is because very few teams could actually do what was required in the rules, which was to cross the finish line with more or at least equal the energy that you started with. And the car you're looking at right here crossed the finish line with about 25% deficit. So they looked at the charge in the batteries, and we were not able. So we couldn't drive this thing indefinitely. We actually did drain the batteries during the race, and the primary reason for that was our transmission, and I'll take a lot of the blame for that. We used a double inverted bicycle transmission because the motor that we used, and again, no blame on the motor, it was a fantastic motor. The motor that we used, its sort of sweet spot was 10,000 RPMs, and the sweet spot going 20 miles per hour is about 600 RPM. So we had to gear it down substantially, and it was really bogging that motor down. So if we had slightly different motor, better transmission, we would have had a better turnout. But it was an impressive, very impressive vehicle. All right, so let's dig into this Shell Eco Marathon. And it's pretty impressive. Some of these cars, and you use the word car loosely because they're just kind of little vehicles, or what am I looking for? Kind of glorified soapbox derby rigs get thousands of miles per gallon. I got 100, thousands of miles per gallon. And I don't remember exactly what the record is, but some of them might even be pushing, the 10,000 mile per gallon. So I don't want to beleaguer this site. There's way more than we could possibly cover. But here are the other. So we got South Africa, Asia, Europe. Here's fuel efficiency. Maybe we'll just take a look at that. Fuel efficiency has increased 4 times since it began in 1985. Maybe they'll have a list of records. Okay, in 1985, the winning vehicle would have been efficient enough to travel from Rotterdam to London on 1 liter of fuel. assuming that it was flat and they didn't have a headwind. I'm guessing that's part of the deal too. 2551 kilometers per liter. Let's turn that into miles per gallon just as a little exercise here. So we'll just do that. That'll be our first little fun math of the semester. If you guys want to follow along and try this with me, you're more than welcome to. So 2552, let's call it. This is kilometers per liter. 2552. Did I write that out? Yeah, 2552 kilometers per liter. And now let's do kilometers per mile. And then we can do liters per gallon. And liters per kilometer. So first, well, you guys go ahead and work. I'll just work kind of quietly here, and then I'll explain myself. Liters per kilometer. Wrong, but let's just try it out. No, we did that wrong. Gallons per liter. Miles per gallon. Liters. Oh, yeah, I did that wrong. Okay, let's do it this way. Got a little too fancy. That doesn't seem right either. It's a little low. Miles per gallon. Let's see. Let's go back to our original assumption. 2552 kilometers per liter. Okay. Well, let's do it in baby steps so we don't make a mistake here. And I'll do it down this way, kilometers per liter. Let's do kilometers per gallon equals that okay, that seems correct since a gallon is larger. Okay, there we go. And then we'll go miles per gallon. Miles per gallon equals that times that. It's going to be a little bit less. Okay, that's more correct. Okay, so right here, if we start with 2552 kilometers per liter, that's just exactly what's posted on the website, 2552 kilometers per liter. A gallon is greater than a liter, so if you put a gallon in there, you're going to go about 4 times farther, and that's exactly what that is. So almost 10,000 kilometers per gallon. That's what I was kind of thinking, because I knew there was a 10,000 in there somewhere. So it's almost 10,000 kilometers per gallon, which is not conventional. But turn that into miles per gallon. Obviously, the mile is longer, so you're going to get fewer miles than you would kilometers. So 6,000 miles per gallon is the current. I know, it's crazy. Okay, so that's where the combustion vehicles are. Going back to the solar car, it's essentially infinite miles per gallon, right? If you keep going, you're not, because you're consuming energy just as quickly as you're making it. Okay. What else do we need to know? I did mention urban concept versus prototype. Let's go back. Let's go back and see if we can't find the rules here. The rules are fairly static, but they change each year a little bit. And I'm certainly hoping that the vehicle that we built last year still fits within the parameters. It's not too tall, not too wide, not too heavy. So let's hit participants. General information. Okay, there we go. Download the 2016 rules. You know, and building the car is a really fun challenge, but man, it's impressive going to these events and seeing what other teams come up with too. That's where a lot of the education, at least in my mind, comes in.
Or a lot of them like trying to do really high-tech specific stuff like Purdue?
It depends. You'll see some teams with some pretty big budgets that can go pretty high-tech, and then you'll just see some high school show up with a solar panel slapped on a not a Pinewood Derby, but a soapbox car, and that's about it. So the whole spectrum's there. Yeah.
It's not like to try and find something for the masses, kind of.
That's a good question. The vehicle that we built in 2014 was kind of a one for the masses, and you've probably heard of is it Tata? Is that the car out of India? They were trying to make a, and I don't remember if it was electric or diesel or what, but they were trying to make a car for the masses that was just a couple $1,000, and that's kind of the same philosophy we were going after. In a lot of ways, you might think, well, God, isn't that a step backward? Aren't you kind of going back to the whole Henry Ford model? Well, I don't know, maybe. Okay, so here's 51 pages. I'm just going to save this as courses, And I'm going to scroll down into our capstone course 2016, and I'll save this as rules, and then I'll go back and documents, courses, NRGY 299, capstone 2016. So the way this typically breaks down is, obviously the car is comprised of multiple components, multiple systems, and what we typically try to do is assign a student to each component. Like someone's going to be on the drivetrain, someone else is going to be on the steering, someone on the brakes, someone on the body, someone on the frame. And that's really how any auto manufacturing facility works as well. I mean, someone's doing the tires, someone else is doing the paint. So the rules tend to break down in a similar fashion. So these are the global rules. These are the rules that all teams have to follow. We've not been. Oh, so show me. Yeah. So London is where the European, Asian, American champions are. So if you win the Asian or the American competition, then London is where the final competition is. So again, they're in Detroit, Michigan. Oh, pretty cool. The Philippines, in Manila. That's kind of cool. That's a nice message. Okay, so we've got, what is that, 78 different articles. And we're not going to do it today, but I think what we'll do next week is, and in fact, I think this will be a good assignment, is just read the rules. And when I've talked to the organizers before, they said as boring and painful as it is, you kind of just got to read the rules out loud to each other. And once you've done that, it kind of sticks in your head better than, so we'll do that next week. Text in red, change edition, and Lee Curran fortunately has a fantastic memory and has most of this in his head for immediate download. Faculty advisor, that will be me. Track marshal, field marshal, technical director. Entry or two. All right. So logos is a deal. They've been pretty nice in that they've put the highlights in red. Let me see if I can grab Jake real quick. Jake.
Take the 101, 102?
I'm taking both of them right now.
Oh, okay.
Yeah. Just my schedule kind of worked out. Taking both at the same time.
Yeah, why not?
You said you did last year?
Yeah.
Are you energy technology?
Yep.
Yeah, nice.
I just took like the electronic class AC and DC
Yeah.
last year.
Okay.
And the 101, 102.
Yeah.
Right now, it's just some of the electives.
Okay.
Got to finish trigonometry at the main campus.
All right. What electives are you doing?
This semester, actually, I'm only doing internship.
Okay.
Which I'll find out about Friday, and then, believe I'll take probably recycling next semester.
Okay.
Maybe the geothermal.
All right. Is that what you're kind of interested in?
I'm thinking, I had the idea of like energy efficiency, like
Okay.
maybe going to like old houses and doing a blower door
Yeah.
test.
They have some electives on that, don't they?
Yeah, like, I don't think there's one for the fall, but I think this spring, I think they do the building efficiency.
Oh, okay. So yeah, you can finish up next semester then?
Actually, I'll be going through till the fall.
Okay.
Not going real fast, but
Yeah.
should be cool.
Nice.
All right, hey, sorry to abandon lecture there. I just saw Jake, and I wanted to make sure he was aware that we're meeting. It sounds like he can't make the Wednesday, Friday, but,
Actually, trigonometry.
yeah, cool. And it sounds like he's got a pretty tight schedule, but he is willing to help, so. All right, protests. I just want to look at some of the things that can be deal breakers on this. Oh. So the weight of the driver obviously is an issue. A lighter person in general.
Like 2.2 kilograms.
Yeah, so that's I'm gosh, I think I weigh about 90, so I'd be kind of be on the heavy side, but so if you don't weigh enough, they stick a ballast in there, so everyone's got at least the same driver weight. So there's helmets, face shield, racing suit, yeah. Driver comfort. Not as big a deal in Detroit. It's not as hot as Houston, obviously, but good to stay hydrated. Tools, materials, fire extinguisher, battery charging bag in case your lithium battery catches fire, fireproof blanket. And they are really big on safety, and I don't think they've had any problems. I've seen a few wrecks, and they can be a little dramatic, but I've never witnessed an injury or heard of one. So exactly 4 wheels, that's where we are. And we've got a 4-wheel vehicle, and then the frame's actually sitting out in the bullpen. We should go check it out after class here. Continuous contact the run. You can't stick a sail. You can't have a sail in the car, more or less. They're pretty serious about the safety. Just nothing too sharp. That's your minimum radius. And this can be a deal breaker too. Having something that might look safe, but if that radius is too pointy, I don't want a spear on the vehicle either. Energy compartment should be easy to open. Solid floor, that's a big deal as well. Fully covered. So I'm not even sure our vehicle from 2012 would qualify. It was pretty open, as you saw there.
the mono?
Monocoque frame means that it's like a shell rather than tubing. It just, so I don't know if you remember back in the days of bicycle building, there's some of the first monocoque bicycle frames came out where rather than welding tubing together, they just had a single carbon fiber frame that was done all in one layup, so it's just one piece rather than having any seams. That's what that is. We do not have a monocoque design, so. Roll bar, I think we're all set for that. We should go check it out. Static load, 70 kilograms. They'll hang something on there to make sure the thing doesn't bend in on you. This is a big deal, the bulkhead, just so that the driver is safe from the moving parts of the transmission, etc. It also has to be fire retardant. This is a big deal too, that you can sit in there and see out easily. And I think probably the next thing for us to do would just be to take these rules, stick them into an Excel spreadsheet, and just check them off when they're done. And if they're not, just leave them open until they are. I think that's a good verification step to do.
Always update the flow chart.
Yeah, exactly. Technical inspection, weather visibility. Jake actually mentioned he would be willing to work on the windshield wipers. He put some time in on that last season, so we can hit him up for that again. Safety harness, five-point mounting. We have a lot of this equipment already that we can cannibalize from previous cars. Urban concept, prototype, emergency services, hinged attachment. Prototype's not a big deal for us. So for urban concept vehicles, the opening and release mechanism must be easily, intuitively operable from the inside and the outside of the vehicle. We had a pretty good set of doors last year, and we can replicate that. Red arrow, got to have a horn, has to be loud. Onboard fire extinguisher. Driver position. So when you sit in there, you can't be squished up against the top. So this does not apply to our electric vehicle, but you can't have a thing that's just always moving or always running. Yeah. That's the exhaust, not a big deal for us. You can't be too loud. These are, so there actually is a compressed natural gas category too, kind of cool. Here we go. So the battery electric vehicles must provide a physical isolation with propulsion battery from the vehicle system. Like normally open contact type. Internally. So this is so if the driver can shut it down, or if the driver is incapacitated for whatever reason, it can be shut down from the outside. And again, dead man switch. Directly. So this is kind of new. It's like it's a switch in series with the accelerator. So in addition to moving the accelerator, you have to have this button on the whole time. And if you take it off, and it's like a lawnmower. It's like that the little lever you might see in a lawnmower. Sometimes if you let go, the thing dies. Okay, so here are the dimensions. That's for prototypes. So we can just kind of skip through that. Braking. Here's urban concept. You got to be at least a meter tall and not more than 1.3 meters tall. There's the width, there's the length, There's the track width, the wheelbase. We'll go out and make sure that all of our dimensions are correct. You can't be too low. You can't be too heavy. Just talked to Jake. He said the frame is super light. He's really impressed with it. Vehicle body. Windscreen with wipers. Got to have a little luggage space, not too big. The luggage must be supplied and be in place. It could just, be a milk jug or something like that. Towing hook or ring, you have to have that. The wheel cannot be too large, or sorry, too small. Turning radius 6 meters or less. That's actually pretty generous. That's a pretty big, that's, 18 feet. That's, turning around in a 36-foot wide road. There's the wheels cannot be too big or too small, and we do have some wheels. We have to make sure they're appropriate. Driver cannot touch the wheels. The tires have a certain dimension as well. Lighting. This is very important too. If you fail any of these tests, you can't go on the road. Single brake pedal. You have to have 4 hydraulic disc brakes, and we do have those on hand. Master cylinder, brake system, parking brake. So yeah, I think the next step is to get this into one spreadsheet and just start checking the boxes. All right, so we're not doing any combustion. We're going battery electric. Maybe down the road sometime we do a hydrogen. We do have a hydrogen fuel cell, but it's big and bulky and made for stationary. Just don't have anything of that small size. But that'd be a fun challenge down the road. So here are kilometers per kilowatt hour. I said a second ago you might do kilometers per megajoule, but you can just do the same conversion there. And the joule meter is provided, as I mentioned before. In the case of hydrogen, they're using flow cell meters or flow meters. 48 volts, that's where we are. More voltage is better for getting off the line quicker, a little more torque, starting torque in general. We are allowed to use capacitors as well. I think one of the students mentioned that he might have some capacitors we could use. We do have 2 different sets of lithium-ion batteries that we can use as well, and a battery management system. And we'll get into this in more detail. Metal tray is required. I think we had something wooden last time, but obviously have to go with metal. So you can have a small battery for if you've got a radio, a GPS, data loggers, but not headlights or turn signals. we'll need to get, and we do have a good start on our technical documents. We've got last year's report that's pretty far along that we can buff out and put in. And this is how energy flows through the car. Battery electric. This is going to be our main electrical wiring diagram, and I think Colton had a really good start on that, so we can just use that and go from there. Same thing on the propulsion block diagram, how energy flows through the system. Battery electric, so we need each of these separate wiring diagrams, not a big deal. I have to just provide all the specs on what we have for the batteries and the battery management system. Fuel cells, supercapacitors, motor controllers. Okay, so this internal combustion does not apply to us. Fuel tanks does not. Fuel system does not. Hybrid technology. We have not really decided whether or not we're going to use a capacitor. Like I said, one of the team members for this year said he has access to these, and it might turn out to be to our advantage. You cannot store energy mechanically or hydraulically, only electrically. And so if you're storing, not sure why well, I guess a capacitor in addition to the battery would be your stored energy, obviously, because you have to start with the battery on board. Oh, and I think they want you to label this too, because the capacitor obviously can discharge much more quickly than a battery, so you can get a much bigger zap in a hurry from a capacitor than you could from a battery potentially. And they want to make sure that the supercapacitor is not charged at the beginning of the race. It's just for on-board running time storage and maintenance. Starter, it's for ignition, electric propulsion, fuel cells, hydrogen cylinders, ventilation, hydrogen detector. Wiring, clearly distinguished. So this is a pretty big deal, making sure that the wiring is neat. We've always done a pretty good job with that in the past. Making, you've got your propulsion power and your accessory power, and obviously two very, a lot more juice flowing through the propulsion than the accessories. Fuse.
Different colored zip ties.
Yeah, different colored zip ties would be fine too. You can have up to 2 electric motors. We've got multiple motors. We've gone through a bunch of different iterations. It's amazing how hard it is to find a motor too of the appropriate size and RPMs. But we do have a good selection. Modifications. Okay, so the motor controller must be purpose-built for the Shell Eco Marathon, and this is a tough one. The electric motors may be purchased or purpose-built. The motor controller must be. So we have to build our own motor controller. There's been a few cases in the past where if a team buys a motor controller and does a slight modification to it, they allowed it. But this is the new deal. That's not allowable anymore. So we'll just have to see where we are. That's going to be one of our more challenging builds. So motor controllers built from subcomponents. So here's an opportunity for a little bit of reverse engineering, because we do have a couple purchased motor controllers, and it's basically going to come down to seeing what's in there and then, more or less recreating it. Probably not as sophisticated as a commercial, but if you're using other subcomponents, then it's fine. And we do have the ability to etch SEM in our little lab next door. We can do some etching of that. Only lithium ion, fine, we're good there. Batteries and the bulkhead, no on the bungees. Here's where the joule meter goes for measuring energy. Electrical circuits, protected, starting line, finishing line, fuel marshals. Internal combustion, that's not us. Methane detector, methane, no. Okay, so, there's a little bit of money involved if you win. Prize money, trophy, onstage winner ceremony. Natural gas. So battery electric, same deal. If you win, there's $2,000. Oh, and even third place gets $500. Off track. We've done this in the past too. It's kind of nice to participate in this, and it's a good. It works in well with the curriculum. It's just a little bit of write-up on, the philosophy of the event. Safety would be nice. Preservation spirit would be nice. Since we've competed this before. Okay, so we won't go through all this. We can kind of deal with that later. But okay, so there's kind of a big, broad overview of the race, and obviously we kind of hurried through the rules. But I think the next thing to do as a team would be to break down every one of these sublines in Microsoft or Excel, for example. Cut out the stuff we don't need, keep the stuff we do for our car, and then just kind of go down and just use it like a checklist and where we are in each thing. All right. Well, that's it. So I'll wrap up that little chunk, and I think that was going to be that was almost an hour I just went for. And then we'll just spend another, well, I guess we've been here for about an hour and a half. We'll just spend another 20, 30 minutes going over where we are with the car right now and seeing what you guys are interested in. So.